Hello, welcome to my podcast on chapter 9e about groups, and I will make several screencasts on this chapter, and this is screencast number 1. I start with a very simple idea which is called algebraic structure, which is a set with one or more operations. Think about the set n and the operations addition and subtraction. Remember, you were in primary and you learned to live within this structure, and you could count and make exercises like 1 plus 2 equals 3, and you came home and told your mother that you knew what 1 and 2 was, and you lived happily in this mathematical village. And then you discovered that it not always worked like that, because 7 minus 10 was all of a sudden a problem. So you learned the world was bigger than your village, and there was this country, and this country was part of a continent, and this continent was part of a global mathematical world, and this global mathematical world was part of a solar system. And by that time you were on the secondary school, and we lived happily in our mathematical solar system. Now, in the meantime, we understand that there are several solar systems, and we looked at the basis of all these systems because they have the same fundamentals, like binary operations, like sets, like relation. And now we take the next step, because we are going to leave all these solar systems which forms a galaxy, and we go into another mathematical galaxy, and the term for that is group. Now, in the meantime, we struggle to keep with the relation with reality. Basically calculating with your fingers 1 plus 2 equals 3 seems light years away. Well, anyway, that's life, so let's start on our galaxy trip in our starship. And I'm going through several definitions to start with, and then we'll go on from there. So the first definition is algebraic structure, which I already mentioned. Now, if I have a special algebraic structure with only one operation, I'll call this a groupoid. A groupoid where the associative law is obeyed. You know what this is. We call a semigroup, and if this semigroup has an identity element, it's called a monoid. And now I come to the definition I really want to use in this chapter, and that is the definition of group. Now, a group is a non-emptive set G with a binary operation star, which is defined with the following axiomas. By the way, this group I can write like G, comma, star between these scribbled brackets. Now, what are these 4 axiomas? First of all, G needs to be closed. Secondly, star needs to be associative. Star needs to have an identity element, and each identity element needs to have an inverse, being for instance, if I have a to inverse times a, that then the result is my identity element. Now, if these 4 axiomas are true, then this group G in combination with the operation star is called a group. Now, in addition to that, if also the commutative law is obeyed, this is a special group, and it's called the Abelian group. Now, having defined the groups, I'm going to look at two theorems, and the first theorem is about the cancellation laws. And the theorem is that exists from a left cancellation and a right cancellation law, which means if I have A star B equals A star C, then B needs to be C. So you can cancel A out. And obviously the right cancellation law, then A is on the right side and you have exactly the same. Now we can prove this law by the following argument. If I have B star A equals C star A, then I can multiply both sides of this equation with A to the minus 1, which leads me to the equation B star A star, this is an A to the power minus 1, and here this. Now, and because the associative law is part of the axiomas we use for the groups, I can apply it here by calculating this first, and then I know that A star A to the minus 1 gives me the identity element E, and there as well, and therefore B times E gives me B star E, I need to say, it gives me B, and C star E gives me C, and there we have it. Now the second theorem is about Cayley tables, which we already discovered working on binary operations, and now we apply the same idea for groups. And the theorem we are looking at is the following. If I have this group G with operation star, then each element of G will appear exactly once in every row and once in every column of its Cayley table. And that's what I would like to show you how this works. Now suppose I have an element A, which is an element of G, and I have another element P, which is also an element of G. Now here I have the Cayley table of the star operation, and here I have the element A. And in this row I have the element P, both elements of G. Now what would be the element that I would need to have here? Well, obviously A star, whatever I write here, needs to result in P. Therefore I can write here A to the power negative 1 star P. And since A to the inverse operation was also a part of G, this element again is also an element of G. Then again, I know as well that since this element only appears in G once, that P also will be appearing in this row only one time, because a little bit further in the row I have maybe a different element of G, Q, which is the result of A star A to the power negative 1 star Q, which again is also an element of G, and so on. So you see, in this row P will only appear once, Q will only appear once, etc., and so forth. So this proves that every element will exactly appear once in every row. a similar train of thought you can develop for the column, which in the end proves the theory.